Okay, in this lesson, we're going to be reviewing our compound interest formulas and learning about calculating ordinary annuities. Let's start with our compound interest formulas. We've seen these before. These are useful for compounding interest over a certain time period. We'll start with our compounding over a certain compounding period formula. This is our A equals P times 1 plus R over N to the NT formula, where A is our new or our final amount, P is our original amount or our principal amount, our down payment, R is the interest rate as a decimal, N is the number of years the interest is calculated, number of times a year the interest is calculated, and T is the number of years the money sits in the account accruing interest. Okay, so this one's useful for problems where you see the phrase compounding monthly or compounding daily or weekly or biannually. So in example number 1, it says consider the situation where n equals 1. So after we do example 2 together, I'd like for you to try example 1 in your notes on your own. Okay, so it talks about what does it mean in the context, and what is your formula going to look like when you substitute 1n for n? Okay, but let's do example 2 first together. So that says Victor deposits $500 into a savings account earning 6% interest compounded monthly. So there's that key phrase that lets us know which formula to use. And it says how much money is in his account in 12 years. So we're going to need to use this formula here. And let's break down what we're given in this problem. Okay, so depositing $500, that is our principal amount. So our p-value is 500. This 6% is going to be our interest rate. So now remember, we want our interest rate as a decimal. So we're going to move that decimal to the left 2 places. So our R value is 0.06. We're told that we're compounding monthly. So our N value is 12 months in a year. And it's going to be in there for 12 years, so our T value is 12 as well. Okay, so let's plug in what we know into our formula. So we're looking for our final amount A. Our principal is $500. We're multiplying that by 1 plus our R value, 0.06, over our N value, monthly is 12. And we're going to raise that to that same N value again, times our T value, which is also 12 in this problem. Okay, we've gotten rid of all of our variables on the right side. So this is the point where we go to our calculator and we carefully plug this into our calculator and see what we get. Oops. All right, so we've got, let's see, where were we? We've got 500 times, in parentheses, 1 plus. I'm going to use the fraction function. If you don't, just be careful with parentheses in doing these hairy formulas here. So I've got 0.06 over 12. And all of that is going to be raised to the 12 times 12 power. All right, and we end up with 1,025, and we're going to round to the nearest penny for these finance problems. So that's the hundredth. So $1,025.38. All right, that's not too bad for starting off with $500. Okay, our other type of compounding formula is our compounding continuously formula. All right, so this is the formula you've probably remembered as the PERT formula. So we say our final amount after or over time is our principal times e to the RT power. Okay, our variables represent the same meanings as in the previous problem, and we just have the introduction of this e, that natural constant, as our base to our exponential here. All right, so let's look at an example. In example number 5, we've got Bob who invests $500 into a savings account earning 6% interest, compounded continuously. So here's that phrase that points us in the direction of the formula that we want to use. All right, how much money does Bob have in 12 years? Okay, so we've picked out our variables, we've picked out our formula, so let's plug in what we know. We're looking for our final amount after 12 years. If we deposit a principal of $500 at an interest rate of 6% over 12 years. All right, again, we've gotten rid of all of our variables, so let's plug this into our calculator. So a couple dollars more, almost, than if we were in a similar account, but that compounded monthly as opposed to continuously. All right, so we've now learned and reviewed how to calculate interest compounded over different compounding periods and even compounded continuously. Both of these methods assume that you are investing a principal amount of money at one point in time and then letting it sit and accrue interest over time. So in both of those previous examples, we were assuming that we didn't touch that account over those 12 years. We didn't put more money in and we didn't take any money out. But what if your grandma taught you that every time you get a paycheck to put just $50 of it into your savings account? All right, so that's my grandma right there, okay, and my mom. And my mom used to always tell me that her mama told her every time she got a paycheck, put half of it into a savings account for later. So we're gonna do something similar. Instead of half, we're gonna give that a dollar amount in the examples that we're using. So this brings about a different type of problem, and it's something to consider. Maybe a more realistic type of a problem where you have a part-time job and you're able to continuously put in more money into a savings account at regular intervals. Okay, so good question to consider. How much savings would you have when you graduate from Athens if you were to regularly put in $50 each month from your paycheck? Okay, our current formulas do not allow for this. This is an annuity, which is a sequence of equal periodic payments. The annuity is ordinary if deposits are made at the end of each period at the same time the interest is posted in the account. We will only consider ordinary annuities in this class. All right, so let's look at an example. All right, example 1 says your new part-time job starts today and you get paid on the last day of each month. You take grandma's advice and put $50 from each paycheck into your new savings account, which pays 6% interest compounded monthly. How much will you have in savings after 1 year? Okay, so similar account to what we were using in the previous problems. We've still got 6% interest compounded monthly, like in example number 2 from above. But now we're looking at how much we'll have after 1 year. Since we're not just putting in a principal amount, we're putting in these equal periodic payments of $50 each month. All right, so looking at this timeline, let's say today we open up our account, we have nothing in our account, so we have $0 on day 0. Okay, but at the end of the first month, we get our first paycheck and we put in $50. So at the end of the first month, we've just got $50. It just was deposited in there. It hasn't had any time to earn any interest. But we work another month, and at the end of the second month, this $50 has been earning interest, and we also put in another $50 from our new paycheck. Okay, so now we've got this 50 plus this 50 from last month plus whatever interest it's accrued. Moving on to month number 3, this original $50 is earning interest over the past 2 months. the $50 from last month's paycheck, and now we put in another 50. You can see how if we were to calculate this by hand, it would get out of control rather quickly. So thankfully we have an annuity formula for this. So let's take a look at this formula. Okay, we've got A equals R times 1 plus I to the n power minus 1 over I, where A, again, is our future value, our future amount. R is our payment amount, what we're putting in on that regular periodic basis. N, notice, is slightly different than the N in our previous formulas. It's the total number of compounding periods. Okay, not just per year, but over the total amount of time that we're putting money in our account. And then I is the interest rate as a decimal divided by the total number of compounding periods per year. So this is kind of our R over N from our old formula, all into an I variable. All right, so let's use this to solve example 1. Putting $50 in, so that is our payment amount. So maybe let's list these. We're looking for A. Our R value is $50. Our interest, our I value, or let's start with our N value. Okay, so if we're doing monthly over 1 year, then there's just 12 months in 1 year. If we were doing it for 2 years, then we would put 24 in that place, since it would be 24 compounding periods over that time. Okay, we're just looking at 1 year. All right, and then our I variable, which again is interest rate, 0.06, over the number of compounding periods per year. We're compounding monthly, so that's over 12. All right, so let's take these and let's plug these into our formula here. So we have our final amount equals 50 times, in parentheses, 1 plus our 0.06 over 12. And I think I'll go ahead and put that in my calculator and get a value for that. Okay, so I've got 0.005. Notice this is without rounding. If this were to extend across my calculator and it looks like it keeps on going, I wouldn't want to use a decimal in this place. Okay, but since this is a nice even 0.005, I'm going to use that here. Okay, that's raised to the n power. Don't forget that minus 1 on top, all over that I value again. Okay, so we've gotten rid of all of our variables on the right side. So I'm going to plug all of this into my calculator and see what we get. All right, which is nice. Putting $50 in our account each month over a year. It's not too shabby. Thanks, Grandma. All right, example 2, if you would, do that one in your notes. When it says how much we have in savings when you graduate from Athens, I want you to actually calculate how many months it's going to be until you graduate, until you expect to graduate. Okay, expect it's going to be June in 2018, 2019, 2020, whenever. All right, and let's look at one more example together. Let's look at example 3. All right, example 3 says you have plans to hike the entire Appalachian Trail the summer you graduate. All right, so the Appalachian Trail, this was something that I always wanted to do, and never did the whole thing, only did a little piece of it, was to hike the whole Appalachian Trail. They call it through hiking, from Springer Mountain, Georgia, all the way up to Mount Katahdin in Maine. So a lot of people do that, or a handful of people do that over the nice weather months, kind of surrounding summer. But it takes some money. You gotta plan out your food. You gotta have decent gear in order to stay on the trail for 4 or 5 or however many months it takes you. So if that's my goal, and I want to do it right after I graduate, then I need to start planning now. I need to start saving now. Okay, my goal is to have $3,000 to spend on gear and food. how much from each paycheck do I need to deposit each month in order to meet my budget goal? Okay, for this problem, I'm going to assume that I'm a junior and that right now it is October 1st, 2017, and that means that I'm going to graduate in June of 2019. Okay, just for the purposes of this problem, let's say that's our setup. Okay, so that means there are 20 months between now and graduation that I can be saving towards my $3,000 budget goal. All right, so because I'm going to be putting in money regularly from my paycheck, then we're going to use our annuity formula and not our normal compounded interest formula. All right, and so using this formula, we know our final amount. We want our final amount to be 3,000. So that is the left side of our formula that we already know. What we want to know is how much of each paycheck do we need to be depositing. So that's our R value. That's our unknown in this case. Okay, building out the rest of our formula, we've got 1 plus. We're using the same account that we had up here in example 1. So our I value is going to be 0.06. We're still compounding, we're still compounding monthly. So let's see, how about we just go ahead and use that same 0.005. Okay, and we're raising to the n power. So total number of compounding periods, that's our 20 months. That's how long we're going to have that account open. And at the end of 20 months is when we hope to have that $3,000. So I'm going to put that 20 up there. Don't forget that -1. And in our denominator, we've got that interest rate divided by 12 again. Okay, so in this formula, our variable is not a loan. So in order to get it a loan, we need to either divide both sides by this, or we can multiply both sides by the reciprocal, which is what I'm going to do. Okay, so we've got R equals, we've got our 3,000, and if we multiply both sides of this equation by the reciprocal of this, then we're going to have times 0.005 over 1, we can just say 1.005 to the 20th power minus 1. All right, going back to my calculator. All right, and we get for our R value, we get 142.999, so I'm going to round that up to an even $143. Okay, which is still rounding to the nearest penny. Okay, so make sure you still round in the nearest penny. Just happened to be in this case, I was rounding the nearest dollar as well. All right, so that's not bad, $143 each month. I need to make sure that I've got a decent job that pays a lot with the right number of hours I can balance my classes with. Got a plan. All right, so we reviewed our compounding continuously formulas, our PERT, and our compounding over different periods formula, and we learned a new annuity formula, which gives us a little bit more freedom, a little more realistic formula for an actual savings account. Make sure that you try example 2 and also example 4 in your notes for class the next day. We'll talk about these, take any questions that you might have.